Welcome to The Explainer. Today, we're diving straight into the fascinating and, honestly, almost invisible world of industrial safety. So imagine for a second that you're tasked with building a massive pressure vessel for a chemical plant. We're talking about giant, towering metal structures that have to handle extreme temperatures, intense pressures, and some seriously volatile substances. How do you guarantee to the plant operators and, the communities living right next door that this massive piece of equipment is entirely safe? And here's the kicker. How do you do that without accidentally ruining the equipment in the process of checking it? It's a brilliant engineering challenge, and today we're going to explore exactly how they solve it. So I really want you to think about this fundamental dilemma. How can we test the ultimate strength of a finished product without breaking it? Look, if you're building a paper airplane, you just throw it to see if it flies. But if you're building a multi-million-dollar industrial vessel, you can't exactly push it until it explodes just to find out where its limits are. You need a way to verify the safety on finished, highly expensive equipment. You have to confirm the structural integrity of the steel and the welds, all while leaving the equipment perfectly intact and ready to go.
Okay, let's get into it. If you've ever studied mechanical engineering, you're probably pretty familiar with destructive testing. You've got things like the tensile test, which literally grabs a piece of metal and just pulls it until it violently snaps in half. Or the Sharpie impact test, which swings a heavy pendulum to see how well the metal resists a sudden shock. Now, don't get me wrong, these tests are absolutely crucial for verifying raw materials in a lab setting, but they are completely useless on a finished product. I mean, obviously your client is not going to be too thrilled if you deliver a broken machine. Once you've welded a giant steel plate together, you can't just rip it apart to see if you did a good job. So, naturally, engineers needed a better way. Enter NDE, non-destructive examination. It's exactly what it sounds like. It's the process of inspecting a material for hidden defects without damaging its original form. Honestly, the best way to think about NDE is like the ultimate medical checkup for machines. When you go to the doctor because you think you might have a broken bone, they don't slice your arm open to check, right? They use specialized tools to look inside you completely harmlessly. Well, in industrial fabrication, engineers are doing the exact same thing to steel. In the field of plant equipment engineering, there are basically 4 primary methods used to perform these mechanical checkups. You can kind of think of them as the Fantastic Four of NDE: PT, MT, UT, and RT. Now, don't worry about the alphabet soup just yet. We're going to break each one of these down. What you really need to know right now is that engineers divide these 4 techniques into 2 distinct categories based on what they're hunting for: surface inspections and internal inspections. First up, surface inspection. This is all about finding those completely invisible scratches. Because before we can even think about looking deep inside the metal, we have to make sure the skin of the equipment is totally free of flaws. Which brings us to our first method, PT, or the penetration test. It's super simple but highly effective. Let's say there's a microscopic crack on the surface. We're talking sometimes thinner than a human hair. Engineers spray a highly visible bright red liquid dye right over the area. Through capillary action, this liquid actually seeps deep down into those invisible cracks. After wiping the surface totally clean, they spray a white developer over it. This developer acts just like a sponge, pulling that trapped red dye right back out. And bam, suddenly a totally invisible defect is bleeding red against a stark white background. It's incredibly reliable for catching surface flaws. Our second surface method is MNT, the magnetic test. And I love this one because it feels a bit like an industrial magic trick. First, you run a strong magnetic current right through the metal. If the metal is perfectly solid, the magnetic field flows smoothly. But if there's even a tiny surface crack, it interrupts the field, forcing some of that magnetic flux to actually leak out into the air. Next, you dust these incredibly fine iron particles over the surface. Those particles are instantly drawn to that magnetic leak, and they cluster right over the crack, vividly outlining the hidden defect. The only catch? Obviously, it only works on metals that can actually be magnetized, like carbon steel. All right, so let's see how this all builds together. We've covered our surface methods, PT and MT, and they are fantastic at catching external cracks. But think about a massive pressure vessel with solid steel walls that are several inches thick. What if the surface is perfectly smooth, but there's a dangerous void, maybe a bubble of trapped gas, lurking 2 inches deep inside that solid steel wall? Surface methods are going to completely miss it. We need tools that can literally pierce through solid metal. And that takes us straight into the second phase of our mechanical checkup, internal inspection. Looking beneath the surface, this is where we hunt for those deeply hidden problems that could cause a massive, catastrophic failure under pressure. The first of our internal tools is UT, the ultrasonic test. If you picture a medical ultrasound used to look at a baby, or even a submarine pinging the ocean floor with sonar, UT works on that exact same principle.
An inspector places a probe on the steel that fires these incredibly high-frequency sound waves deep into the metal. If the metal is solid, the sound just travels straight through. But if it hits an internal crack or a hidden pocket of air, the sound wave bounces right off of it and echoes back to the probe. By measuring exactly how long it takes for that echo to return, engineers can pinpoint not just that a defect exists, but exactly how deep inside the metal it's hiding.
The final member of our Fantastic Four is RT, the radiographic test. Now, this is the real heavy hitter of NDE. It is literally an X-ray for metal. Engineers shoot powerful X-rays, or sometimes even radioactive gamma rays, directly at a weld. These rays pass right through the solid steel. Just like when you get an X-ray at the hospital for a broken arm, a piece of photographic film is placed on the opposite side of the metal to catch the rays coming through. Because a crack or an air bubble is less dense than solid steel, more radiation passes through that specific spot, creating a darker shadow on the film. So you literally get a photograph of the inside of the weld.
Now, what's really fascinating here is the unique geometric reality of doing an RT. Performing a radiographic test actually requires access to both sides of the metal. You have to shoot the radiation from the outside, and you absolutely must place the recording film on the inside, directly behind the weld. This means RT is absolutely perfect for butt welding, where two plates just meet end to end. But it's practically impossible for complex overlapping joints like fillet welds because you simply can't get the film behind the seam. This physical limitation actually dictates how engineers have to design the equipment in the very first place. So, how is all this applied in the real world of plant design? Well, the golden rule for engineers is the total safety combination. To make absolutely sure a pressure vessel won't fail, they don't just pick one test and call it a day. They ensure total safety by mandating a combination. Typically, that means one surface method, like PT or MT, to guarantee the outside skin is perfect, combined with one internal method, like UT or RT, to guarantee the deep interior is totally structurally sound. It's a comprehensive inside-out checkup.
But what happens when the stakes are at their absolute highest? Enter the lethal service rule. If a vessel is going to contain fluids that are highly toxic to humans, engineering codes leave zero room for error. First, all structural joints must be butt welded. No complex overlapping allowed. Why? Because of the second rule, 100% RT is absolutely mandatory. Every single inch of every single weld must be X-rayed. You cannot use UT as a substitute here. You must have hard, photographic proof that no deadly gases will ever escape.
Which really brings us to our final thought for today. If an invisible defect somehow escapes an invisible sound wave or a radiation beam, who pays the price? In industrial engineering, a microscopic crack isn't just a minor inconvenience, it can literally be the difference between a safe community and a catastrophic failure. Non-destructive examination is essentially the invisible shield protecting our physical world. It embodies the ultimate engineering mantra: trust your builders, trust your welders, but always, always verify. So next time you drive past a massive industrial plant, just think about the invisible X-rays keeping the whole thing safely together. Thanks so much for joining me on this explainer, and keep learning.